fiber. So then you have to write the neat block diagram and you have to explain so how the analog electrical signal will be converted to your binary electrical signal, and after that you're going to fed to an optical transmitter. So there, from an optical transmitter we are using an light source. It might be an LED or a laser, so through which you're passing the signal to the optical fiber. So that is your transmitting section. So once it enters into your optical fiber, so there we notice two types of degradation. One we call it as an attenuation and another one is delay distortion. So we know what is attenuation. For three different mechanisms we have lost the signal, and delay distortion is the different components, spectral components will propagate in different velocity, and after some time they will overlap with respect to one another. That means spreading of pulses will takes place, because of which so each of the spectral component will travels with different velocity, and after some time they overlap on one another. That we call it as a delay distortion. So there we need an optical repeater in between. In this block diagram we have not shown. So once again, the optical repeater will consist of a transmitting and a receiving section, where you have to modulate that signal, and once again you have to recast it, and then once again it will be fed to the optical fiber. On the receiving end we can see the optical signal will be fed to a photodetector. It will convert your optical signal to binary electrical signal, and then it will be fed to one of an electronic device called as a coder, and it will convert your signal into binary signal into analog electrical signal, which you can hear on the other end. So this is a telephone conversation taking place between a two telephone users. So how a voice from one end can be transmitted to the other end, however far the distance is. So that is one of the important application of the optical fiber. And also we have discussed about some important advantages and disadvantages of using the optical fibers. So one of the main important advantages too, so we can so the information carrying capacity is more in case of an optical fiber when you compare to the electrical signals, and 10 to the power of more times the signal carrying capacity is more. And here you can transfer the signal whether it is an analog information or it might be a digital information. You can send both however far the distance is, and the lifespan of the fiber is more when you compare with the electrical wiring. So then if you see this circuit, so there is no common grounding. Because of that, we don't have any electrical sparks or shock taking place when you compare with your electrical circuits. And there is no mismatch of the impedance, and no crosstalks can be seen here, and we cannot just swap the information so easily. So these are some of the important advantages of using the optical fibers with respect to the conventional one. And we have certain disadvantages or limitations of using the optical fibers. So among that, splicing is one of the limitations or the disadvantage, because if the breakdown of the optical strands takes place, we need to do splicing. So splicing is little bit risky and expensive also. If the alignment is not proper, so no signal transformation will take place, hence it will be a loss. So that is one disadvantage here. And another one is we cannot bend the cable too hard, such that the cable has to be taken care when you're dealing with the cable at the corners or when you're spooling the cable. So there will should be no such macroscopic bending or microscopic. So that means you should not put too much of pressure also on the fiber, so where arises the radiation loss. So those are certain disadvantages, and because of the temperature variation there might be contraction and expansion of the optical fiber takes place. Because of that there is a loss of signal might arise. Because of the temperature variation the optical fiber will compress and it will expand, because of which there arises some structural irregularities, where therefore there will be no signal propagation. So these are some of the limitations, or we can call it as a disadvantages of using the optical fibers. And that will be the end of this chapter. So today we shall finish off all the numericals, and just I'll brief up with the next chapter whatever that I'm going to discuss with. So I think hardly we are done with 4 numericals. Anybody can tell me? Have you done with this?
No, ma'am.
Yes, then write down this numerical. The angle of acceptance of an optical fiber is 30 degree when kept in air. Find the angle of acceptance when it is a medium of refractive index 1.33. So I hope all of you are kept one book for numerical, compulsory for numerical. In the beginning itself we have told, so all of you have to complete that. So in the sir part, whatever the numericals he has done, you have to maintain in one book, and whatever I have done, you have to write everything. So after the internals we might ask you to submit that by taking the photos of whatever you have written, making a PDF, and you have to send to us. So see that all of you have completed all the numericals. So here the angle of acceptance of an optical fiber is 30 degree, that is theta naught is given. So theta naught is 30 degree when it is in air. Theta naught is equal to 30 degree when the fiber is in air. So find the angle of acceptance when it is a medium of refractive index 1.33. So how will you find out this? So theta naught is given. So when it is in air means n naught will be equal to
Go.
1. So sine 30 degrees
Pa.
how much?
ಕೊಟ್ಬಿಡ ಎಲೆ ಎಲೆ ಎಲ
Sine 30 degree.
ಎಲೆ ಎಲ
Yes, I want some answer from your side. Sine 30 degree.
1/2, ma'am.
Yeah, it is half. So zero point 0.5 sine 30 degrees half. So zero point 0.5 will be equal to square root of n1 square minus n2 square. And n naught will be equal to 1 since the fiber is in air. So zero point 0.5 is equal to n1 square minus n2 square. So if I have the same equation for water, I'll write it as sine theta naught, and I have to find out theta naught when the fiber is in water, or you can write sine theta naught in the suffix, you can write water, or you can write it as sine theta naught dash, where that will be equal to square root of n1 square minus n2 square by n naught into dash. That represents the fiber is in water. You can represent, differentiate that. If it is simply theta naught, it is in air. If I put it as dash like this, so then you can understand that the fiber is surrounded by water. So now if in this experiment, in this equation, you have to calculate now what is theta naught dash. That means when the fiber is in water. So that is nothing but sine inverse of n1 square root of n1 square minus sine inverse of square root of n1 square minus n2 square, the whole thing divided by n naught. N naught dash is nothing but when the fiber is in water. So that is 1.33. So from this above equation, we have square root of n1 square minus n2 square is 0.5. So theta naught dash is nothing but sine inverse of 0.5 by 1.33. See that how much you'll get. Sine inverse of 0.5 by 1.33. How much you got?
22.08, ma'am.
22.08. Okay, approximately I've written here as 22. So first here they have not given n1 and n2. So you have to take up the general expression sine theta naught is equal to square root of n1 square minus n2 square minus divided by n naught. When the fiber is air, in air, so theta naught they have given. So put sine theta naught. So sine 30 degree is half. So half will be equal to square root of n1 square minus n2 square, because since the fiber is in air, n naught will be equal to 1. So, similar equation if you consider for water, so I'll write it as sine theta naught dash, or in the suffix you can write it as water, will be equal to the same equations. So, n naught dash. So, this represents the fiber is in water. So, you have to calculate what is theta naught dash or theta naught water. So, it becomes sine inverse of square root of n1 square minus n2 square by n naught dash. So according to this equation 1, we have square root of n1 square minus n2 square is half. So 0.5 divided by 1.33. So whatever you're going to get, take the sine inverse of that. So you'll get 22.08 degree, right? 22.08 degree. Yes, all of you are done with this. I'll move to the next one. Is done? Is
Sir.
right on the next one. Yeah. A glass fiber is made with core refractive index. A glass fiber is made with core refractive index 1.5, and cladding is doped to give and cladding is doped to give a fractional index difference of, and cladding is doped to give a fractional index difference of 0.0005 full stop. Determine the cladding index. Determine the cladding index, comma, critical internal reflection angle, that is critical angle of incidence, comma, the external critical acceptance angle, means angle of acceptance, and numerical aperture. Angle of acceptance and numerical aperture. Yes, first write down what is a given in the numerical. So they have given the core refractive indices, that is N1 is given. So N1 is 1.5. N1 is given as 1.5. And then the refractional index change is given. So this is delta. Delta is given. Delta is 0.0005. So now we are supposed to calculate. So you are supposed to calculate the cladding index, that is N2 you have to calculate, and the critical angle of incidence, that is theta C, and also the angle of acceptance and the numerical aperture. So we have to calculate one by one. So now first we shall see how to calculate the refractive indices N2. So I am using this equation delta, that is a fractional index change delta equation. So delta is given by n1 minus n2 by n1. So here delta is given. So delta is known and n1 is also known. So from this equation you can calculate n2. Yes, can see that you'll get the value of n2 as 1.499 by using this equation. Delta is equal to n1 minus n2 by n1. Or next you can write delta into n1 will be equal to n1 minus n2. Delta into n1 will be equal to n1 minus n2. Once again rearrange this. Substitute the values of delta and n1. So what will be your n2? N2 will be equal to n1 n1 minus of delta into n1. Yes, what is the answer?
1
Yes,
point
it.
49925.
Okay. 1.499. Up to 3 decimal it's enough. You can stop till there. So 1.499. Okay, now N1 was given and we have calculated what is N2. That is the cladding index. So next comes the critical angle of incidence. So what is an equation? So in the beginning when I am discussing the total internal reflection, I have told you have to be familiar with this expression. The critical angle of incidence theta C is given by sine inverse of N2 by N1. Just now we know we have calculated n2 and already they have given n1. So n2 divided by n1 you do and take the sine inverse of that, where that will gives you the critical angle of incidence, that is theta c. Theta c is sine inverse of theta c is sine inverse of n1 by n2 by n1. It is approximately equal to 1. So tell me what's the answer. 1.499 divided by 1.5.
And 89.87.90 degrees.
Okay. So if you do this, so already I have written given the answers here. So it is 87.9 degree. See that you are getting the same answers. So now we have calculated the N2, the cladding refractive indices, and also we have done with the critical angle of incidence. Now you are left with to calculate what is angle of acceptance and the numerical aperture. So for this, you can take any of these two equations. So if I take the numerical aperture sin theta naught, so we know it is n1 and n2. So from that also you can calculate. So if they are not given the fiber, whether it is in air or water, so it is understood it is in air. So using this, you can calculate sine theta naught. So you'll get the numerical aperture. And then you can calculate theta naught and see that you'll get these two answers. So otherwise you can take the relation between the delta and also the numerical aperture. So sine theta naught is equal to n1 into square root of 2 delta. They have given delta also. So using this equation also you can calculate the numerical aperture and theta naught. So see that you'll get the numerical aperture as 0.0474 and theta naught will be 2.72 degree.
Excuse me, ma'am.
Yes.
Ma'am, if we use the first formula, numerical aperture is equal to sine theta naught, which is equal to root of n1 square minus n2 square by n0, I am getting the answer as 0.0547.
Hmm.
But if we use numerical aperture is equal to n1 root of 2 delta, I am getting the answer of 0.0474.
Okay. There is slight variation, right?
Yes, ma'am.
Okay. No problem. So by using this, you're getting 0.05 something, right? Is all of you done with this? Shall we move to the next one? Yes, if you're done with this, so you check with the answer. So the numerical aperture will be 0.0474 and theta naught will be 2.72 degree. Is write down the next one. Can you see the slide now?
Yes, ma'am.
Yes, write down. Calculate the V number for a fiber of core diameter 40 micrometer. Calculate the V number for a fiber of core diameter 40 micrometer and with refractive indices of 1.55 and 1.5 respectively for core and cladding, 1.55 and 1.5 respectively for core and cladding, when the fiber of the propagating wave, when the wavelength of the propagating wave is 1400 nanometer. Also calculate the number of modes that the fiber can support for propagation and assume that the fiber is in air. Assume that the fiber is in air. So here first you write down what is a given thing in a numerical. So they have given the core diameter. So core diameter is 40 micrometer, that is D is given. So you have to convert it into meter, 10 raised to minus 6. Micro means 10 raised to minus 6 meter. So with refractive indices, so N1 is 1.55 and N2 is 1.5. The core and cladding refractive indices N1 and N2 is given. So then the wavelength of the propagating wave lambda is given. It is 1400 nanometer. So you have to convert this into meter into 10 raised to minus 9. And then you have to calculate first what is a V number. What is V number? And then once you know V, then you calculate the number of modes. So now you use an equation. V is equal to pi d by lambda into numerical aperture, and at the end they have given assume that the fiber is in air. So N naught will be equal to 1. N naught will be equal to 1. N naught will be equal to 1, so that you can remove this term. So you are left with pi d by lambda into n1 square minus n2 square. Substitute all the values there. So V is equal to pi into D. So what is D? You put it as 40 into 10 to the power of minus 6. So pi value is 3.14 into 40 micrometer, 10 raised to minus 6 into 40 micrometer, 10 raised to minus 6 divided by 1400 nanometer. You convert that into meter. So 1400 nanometer into 10 raised to minus 9. Yes, can anybody tell me what's the value of V into 10 to the power of minus 9? I'm converting this nanometer to meter into square root of n1 square minus n2 square. 1.5 1.55 square, 1.55 square minus of 1.5 square. Yes, what's the answer?
35.03, ma'am.
Okay. So if you do this, so this gives you the V number. So pi into d I'm converting from 40 micrometer to meter 10 raised to minus 6 into square root of n1 square minus n2 square. The whole thing divided by lambda. Lambda is 1400 nanometer. Convert that into meter. So we'll get 35.04. 04 or 02? Approximately equal to 35. So this is a V number. So we know that how to calculate the number of modes. Always the number of modes is calculated by V square by 2. So if V is very much greater than 1, now V is very much greater than 1. So that means it is 35. Therefore, the number of modes supported for the propagation is approximately equal to V square by 2. So it is V square by 2. See how much you'll get. So this is the number of modes supported for propagation. Number of modes will be approximately equal to V square by 2. Number of modes is approximately equal to V square by 2. See how much you'll get.
613.55.
If you're 613.55.
Yes, ma'am.
Okay. Here because you have taken here also the fraction 35.02 or 03 you told, right?
03, ma'am.
Okay. So V will be 35.03. So since V is very much greater than 3, 1, the number of modes will be approximately equal to V square by 2. So if you do, you'll get 613.55. So these many number of light rays can propagate through your fiber. So I'll proceed further. Right on the next one. So this is with respect to attenuation coefficient. Write down. The attenuation of light in an optical fiber is 3.6 decibel per kilometer. Are you able to see the slide? So the attenuation,
Yes, ma'am.
yeah, write down. The attenuation of light in an optical fiber is 3.6 decibel per kilometer. Full stop. What fractional initial intensity remains after 1 kilometer and 3 kilometer? What fractional initial intensity remains after 1 kilometer and 3 kilometer? So here we have to see what is a given. So the attenuation of light in an optical fiber. So 3.6 decibel per kilometer is nothing but your alpha. The attenuation coefficient is given, the alpha. So you have to find out what is the fractional initial intensity, that is P out by P in. So after 1 kilometer and after 3 kilometer. So you have to calculate what is P out by P in when it is the L, the distance L is 1 kilometer and when the distance L is equal to 3 kilometer. So first write down what is a given. So alpha is given. So you have to calculate P out by P in 1 kilometer and 3 kilometer. So you have to use an equation. Alpha is given by minus of 10 by L log to base 10 P out by P in. So this is an expression that we are having. So many decibel per kilometer. So now we have to rearrange this equation for P out by P in. So further I'll write. So if I want to rearrange this to write. So here P out by P in, we call it as fractional initial intensity. So P out by P in is fractional initial intensity. So rearrange this equation. So I'll write log to base 10 P out by P in will be equal to minus of alpha into L by 10. So then P out by P in will be equal to 10 to the power of minus of alpha into L by 10. Is it clear? So next we have to calculate. So by putting alpha 3.6 decibel per kilometer and L is already given in kilometer 1. So you can calculate what is P out by P in after 1 kilometer. You have to write it in this way. So P out by P in, P out by P in. In the suffix, you have to
ಅಪ್ಪ
mention
ನೀರ್
what is the
ಇಡದ್ಬಿಡಪ್ಪ
length
ಎದಳಪ್ಪ
of the fiber.
ಅಪ್ಪ
So P out by
ಅಪ್ಪ
P in when L is equal to, so L is equal to 1 kilometer, 1 kilometer. So now you write that will be equal to 10 to the power of minus. So alpha it is in decibel per kilometer. It is 3.6. So what is the length of the fiber? It is also given in kilometer itself into 1. The whole thing divided by 10. So see how much you'll get. So 3.6 divided by 10, it is 0.36. Take 10 to the power of minus 0.36. So you'll get 0.3436. Got the answer?
Yes, ma'am.
Yes. In the same way, you have to put L is equal to 3 kilometers. So whatever the distance that they are going to ask, so you have to substitute L with that value. So I'll write it here. So P out by P in. So at the suffix you write for L is equal to 3 kilometer. For L is equal to 3 kilometer. So that will be equal to 10 to the power of minus 3.6 into 3 divided by 10. So now you take 10 to the power of minus that value. So you'll get P out by P in for L is equal to 3 kilometer will be 0.0832. Yes, got the answer?
Yes, ma'am.
Yes. Now we shall proceed further. So this is an numerical with respect to your attenuation coefficient. So if you're familiar with this expression, so they will ask you to calculate alpha or the fractional initial intensity, that is P out by P in. So if they ask alpha, it is a direct substitution. So they will give this P out by P in two different initial intensity and the output intensity. So you have to put that value. And the distance, if they are given in kilometer, directly you can put it in kilometer. If it is in meter, you have to convert it into kilometer. So directly if you put, you will get alpha. So if they give alpha and ask you to calculate P out by P in, then first you have to show all these steps. So you have to write this equation and you have to write what is P out by P in up to this expression you have to show, and then you have to do the substitution for alpha and L, and then you have to write the final answer. So now we shall move to the next one. So here you can see, here we are going to calculate what is alpha. So find the attenuation in an optical fiber of length 500 meter. Find the attenuation in an optical fiber of length 500 meter, comma, when a light signal of power Just a minute. So here both I have written as 100. So make a correction here. When a light signal of power 100 milliwatt emerges out of a fiber with a power 90 milliwatt. So here you make it a correction. It is 90 milliwatt, not 100. So make it a correction with a power of 90 milliwatt. 90 milliwatt. So here the length of the fiber is given in meter. It is 500 meter. You convert that into kilometer. So length of the fiber. So L is given in meter. So convert that into kilometer. So kilometer means 0.5 kilometer. 0.5 kilometer. So now here which is P in and which is P out? The input power P in is equal to how much?
100 milliwatt.
Yes. So 100 milliwatt is your P in and 90 milliwatt is your P out. So this is P out. Now you can directly substitute and you can calculate the alpha. So alpha is minus of 10 by L log to base 10 P out by P in. Here both the powers are given in milliwatt. You have to convert it into watt 10 raised to minus 3. So when you convert both of them will get cancelled and further you see how much you'll get the answer. So alpha will be equal to minus of 10 by L minus of 10 by L. L is nothing but 0.5 minus of 10 by 0.5. So log to base 10 log of, so 100 by 90, 90 by 100. So 90 P out by P in. So you convert that into watt into 10 raised to minus 3. So in both the cases if you have 10 raised to minus 3 it will get cancelled. Yes, see how much you'll get the answer into 10 to the power of minus 3. Here also 10 to the power of minus 3. So both are in milliwatt and we are converting that into watt. So 90 milliwatt and 100 milliwatt. So both of them will get cancelled. So you're left with 90 by 100. So whatever you're going to get, take the log of that into 10 by 0.5. So alpha. That attenuation coefficient alpha will be equal to so many decibel per kilometer. See that you are going to get this 0.915 decibel per kilometer.
Yes, ma'am. 0.914.
Yeah. Yes, now we shall move to the next one. If you're done with this, you can write this and you can do it on your own. So calculate the numerical aperture as we have done in the previous numerical with respect to the same thing you can calculate. So calculate the numerical aperture, comma, the angle of acceptance, comma, the fractional index change, comma, B number and number of modes in an optical fiber. Calculate the numerical aperture, the angle of acceptance, fractional index change, V number, and number of modes in an optical fiber of core diameter 50 micrometer, core diameter 50 micrometer, comma, having refractive indices 1.41 and 1.4 for the core and cladding respectively. 1.41 and 1.4 for the core and the cladding respectively at wavelength 820 nanometer. 820 nanometer. So as we have done in the previous numerical, so with respect to the same thing, first write down what is a given thing. So the core diameter they have given, so it is 50 micrometer, convert that into meter, 50 into 10 raised to minus 6. And N1 is given, the core refractive indices, and this is N2, the cladding refractive indices. And lambda is given, 820 nanometer. So you have to calculate sine theta naught, the numerical aperture, and theta naught, the angle of acceptance, and delta, the fractional index change, the V number, and the number of modes. So whatever the answers I have written, you just write down that and check with your answers. So delta is n1 minus n2 by n1. See that you're going to get this delta. And use the formula for V number, calculate V and then the number of modes.
Next one.
So you can use sine theta naught is square root of n1 square minus n2 square by n naught, or if you know delta, you can use this also to calculate sine theta naught and theta naught. Is any one answer you can tell me? Is it okay with my answer? So then we can proceed further. Is anybody else done? At least any one or two you can tell me the answer.
Ma'am, numerical aperture 0.167
Okay.
and angle of acceptance is 9.613.
Theta naught is 9 point.
613.
Okay, fine. See that you'll get delta as 0.007. So if you do, you'll get 7 into 10 to the power of minus 3. It is nothing but 0.007. And using this V number, if you calculate, you'll get the V value. So using that, you calculate the number of modes. Is done? Yes, I'll move to the next one. You write down the answer for V and number of modes and check with that answer. Yes, I'll proceed further. Write down the next one. An optic glass fiber, an optic glass fiber of refractive index 1.45 is to be clad with another glass. An optic glass fiber of refractive index 1.45 is to be clad with another glass to ensure internal reflection that will contain light traveling within 5 degree of the fiber axis. Full stop. What maximum index of refraction is allowed for the cladding? So can anybody can tell me how to do this? I have written the answer there already. Can anybody can tell me? So they are given the refractive indices of the N1 is given. So N2 has to be calculated.
Krishna.
So how we are going to calculate? So here you have to use an Snell's law. So if we have an optical fiber, so if this is your optical fiber and this is your fiber axis, so they're telling, so the ray is made to incident, the ray is
ಫಸ್ಟ್ ನೀರ್
made to
ಹಿಡ್ಕೊ ಫಸ್ಟ್
incident.
ಚರ್ಗ ಒಂದ್ ಚರ್ಗೆ ಆಮೇಲೆ ತೊಳೆ ಊದ್ ಬಿಡ್ಬಿಡ ಇದೇ ಆಯ್ತು ಒಂದ್ 4 ಗಂಟೆ ಕುಡಿಯಕ ಫಸ್ಟ್ ಚರ್ಗ ತೊಳೆದ್ಬಿಟ್ಟು
So
ಎರಡ್ ಚರ್ಗ
this is an incident ray
ತೊಳೆದ್ಬಿಟ್ಟು 5 ನಿಮಿಷ
with angle of
ಯಾಕೆ ಸುರ್ರೆ
incidence
ಆಮೇಲೆ
at
ತೊಳ್ಕೊಡ್ತೀನಿ ಬಾ ನಾನು
fiber
ಈಗ ಎರಡ್
axis
ಚರ್ಗ
is
ತಂದಿಲ್ಲ
5 degree.
5 ನಿಮಿಷ ಮಡಗಪ್ಪ ಅವನು ಉತ್ನಲ್
So then
ಇದೆ
at the
ಒಂದ್
core
ತಪ್ಲ
cladding
4 ಗಂಟೆ ಬಳಸ್ತೀನಿ
interface,
ಮಡಗು
so at this interface, so what will be the angle of incidence?
ಈಗ ಎರಡ್ ಚರ್ಗ ತಂದು ಇಲ್ಲಿ ಮಡಗು.
So if a ray is entering into your fiber, so that's what they are telling. So traveling with an 5 degree with respect to the fiber axis. So this is theta 1. So when it enters into the fiber, the angle of incidence is 5 degree. So what will be the angle of incidence at the core cladding interface?
90 minus 5 degree.
Yeah, 90 minus of 5 degree. So this angle will be equal to 85 degree. So 90 minus of 5 is nothing but 85 degree. So now we are applying the Snell's law. So n1 sine theta 1 is equal to n2 sine theta 2. So put it sine theta 1 as 85 degree. So when n1 is equal to 85 degree, so n2 will be equal to 90 degree. It grazes along the core cladding interface. So theta 2 is 90 degree. So n1 sine 85 degree is equal to n2 sine 90. So sine 90 is nothing but equal to 1. So you calculate what is n1 is there given. So sine 85 into n1 if you do, you will get n2. See, tell me what's the answer?
$1.444.
Yeah. So now what should be the refractive indices of n2? It should be equal to 1.44, or it should be less than that, or it should be greater than that for a total internal reflection to take place.
Less than that.
Less than 1.44. So at the after this answer you can write, if n2 is equal to 1.44, if n2 is equal to 1.44, the refracted ray grazes along the interface. If n2 is equal to 1.44, so the refracted ray grazes along the interface, comma, the ray suffers total internal reflection. The ray suffers total internal reflection for n2 less than for N2 less than 1.44. So if it is equal to 1.44, then the refracted ray will grazes along the boundary of the surface interface. So always N2 should be less than 1.44. Then you can expect total internal reflection. So you write down this, and I've given the answer. It is similar to the previous one that we have done. So the attenuation of light in an optical fiber is the attenuation of light in an optical fiber is 2.2 decibel per kilometer, 2.2 decibel per kilometer, full stop. What fractional initial intensity remains after what fractional initial intensity remains after 2 kilometer and 6 kilometer? What fractional initial intensity remains after 2 kilometer and 6 kilometer? So in the previous we have done, so using this equation, so you have to calculate P out by P in for two different lengths. So you have to rearrange that equation for P out by P in is equal to 10 to the power of minus of alpha L into 10, so that at two different length, L is equal to 2 kilometer and L is equal to 6 kilometer. Write down these answers and check with that whether you're getting the same answer. So P out by P in for 2 kilometer will be 0.363 and P out by P in after 6 kilometer will be 0.0479. Write down these answers and check. Is done? Is done? Is write down this last one. So this will be your last numerical. A multi-mode fiber with core diameter, a multi-mode fiber with core diameter 80 micrometer and relative refractive index difference, that is fractional in refractive index change of 1.5% is operating at 0.85 micrometer, full stop. If the core refractive index is 1.48, calculate the number of modes. If the core refractive index is 1.48, calculate the number of modes. Write down the answer. The number of modes you should get around 2825. So can anybody tell me what is the given here? So 80 micrometer is the diameter of the core. D is given. So relative refractive index difference means delta. Delta they are given in percentage. 1.5% means what is the value of delta? 0.0.
1.5.
Yes. Delta you should take it as 0.015. They are given in percentage. So delta will be 0.015 and D is given, that diameter of the core, and this is the wavelength, lambda it is in micrometer. Wherever we have, you have to convert that into meter, and N1 is given as 1.48. So you have to calculate the V number and then you have to calculate the number of modes. So try this. So if you are not getting, so we shall discuss in the next class. So see that the number of modes will be 2825. So this will be the end of your optical fiber communication.
Ma'am, to calculate V number, we need lambda, no ma'am?
Yeah, lambda is given right here, operating at 0.85 micrometer. That itself is lambda.
Okay, ma'am.
This is lambda. Okay, today I'll stop till here. So in the next class, I'll start with the next unit, that is crystal physics. So today this is the end of your optical fiber communication. So in next week, so I'll get the class on next Monday, I think, because Thursday, Friday, Saturday you're having your internals. So the next class I'm going to get on Monday itself. So from next week, I'm going to start with the next unit, that is crystal structure. So I think all of you have seen the timetable and the instructions given to you how the test will be performed or will be conducted. So the syllabus for your internals is quantum mechanics with lasers with numericals. So whatever we have done, so refer to those numericals. So two questions from quantum mechanics they will give. So you have to answer one, and two questions from this lasers you have to answer, pick any one, so that 10 marks from each side, so it will be for 20 marks. So in the WhatsApp
ಏನಿಲ್ಲ
they
ಒಳಕ
have shared
ನೀರ್
everything
ಬಿಡು ಅದು
regarding the
ಇಲ್ಲ
instruction
ಕುಡಿದ್ವಿ
and how we are going to conduct the test. So all
ನೀರು
the
ಬಿಟ್ಟು
best for
ಒಳಗ
your
ನೀರ್ ಹಾಕ್ಬಿಟ್ಟು
first
ಸುಮ್ಮನೆ
internals. If you
ತಕೊಂಡ್ಬಿಡೋದು
have any doubts or any questions, you can call us anytime or you can WhatsApp us. Is it okay? So after I leave the session, sir might give send on more link and he will take the class. So if you have any questions regarding the test or whatever, so you can ask us. So now I'll stop till here. You can just log out from the session and you can join the link that the sir once he sends the link.